Welcome to the Deep Dive. Today we're plunging into a really fascinating challenge in the software world. How can programs possibly do many things at once, faster, more efficiently, without, just collapsing into a mess?
Yeah, it's a core problem.
We're talking about concurrency in Java, and specifically, the powerful Java Concurrent library.
A really essential toolkit.
Our mission today, as always, is to cut through the jargon. This deep dive pulls from a really comprehensive beginner's guide. It helps demystify how applications handle multiple tasks simultaneously, stay responsive, and really leverage modern hardware. We're aiming to give you a clear, concise understanding, so you don't just know what these concepts are, but why they are absolute game changers for building robust applications. Okay, let's really unpack this.
Absolutely. And what's truly revolutionary here, I think, is that understanding these tools is like getting a shortcut. It lets you build high-performance software without having to become a low-level threading expert from day one.
Which is a huge barrier otherwise.
Oh, definitely. It can be an incredibly complex journey on its own.
That's a crucial starting point. So to really appreciate this library, we first need to get a handle on the core concept Java's trying to solve: concurrency. Our source dives right in, defining concurrency in Java as basically a program doing many things at once, using multiple threads.
Right. Threads.
Now, for anyone needing a quick refresher, how does our guide describe these threads? Why are they so central?
Good question. So the source reminds us that threads are these lightweight units of execution. They operate within a program, and crucially, they share the same memory space.
Okay, sharing memory. Sounds potentially complicated.
It is. And that's the key. It's not just what they are, but how complex they become to manage efficiently without the right tools. Think of it like the source uses a brilliant analogy.
Oh, yeah.
Imagine a chef in a busy kitchen managing multiple dishes. While one thing's simmering, the chef isn't just standing there, right?
Right, they'd be chopping veggies or something.
Yeah, exactly. Chopping vegetables, prepping a sauce, maybe baking something else. They're multitasking. It ensures an incredibly efficient use of their time and resources.
I love that analogy. It immediately highlights the efficiency challenge. And the Java Concurrent library aims to solve this, but at a much, much larger scale. We're talking enterprise systems, massive data processing.
Way beyond a single kitchen, yeah.
So connecting that to the bigger picture, our source details some powerful reasons why concurrency is used. What are the big whys here?
Okay, so connecting this, concurrency is used for a few absolutely critical reasons. First, and maybe the most obvious, it lets applications handle multiple tasks simultaneously.
Like a web server dealing with lots of users?
Precisely. Web servers serving hundreds, maybe thousands of clients at once, or programs crunching huge data sets efficiently. That's where concurrency really shines. Second, performance. It drastically improves performance by using multiple CPU cores.
Which almost everything has now.
Exactly. So it's essential for speeding up heavy computations. Third, and this is huge for the user experience, it enhances responsiveness.
Keeping things feeling snappy.
Right. Your application stays interactive. The user interface doesn't freeze up while some big task runs in the background. And finally, scalability. It lets applications grow and take advantage of multi-core processors as hardware gets better.
Okay, that perfectly frames the why. Because if core concurrency is the idea, then the Java Concurrent library is definitely the how for so many developers. It's this collection of powerful tools, classes, utilities introduced back in Java 5, part of java.util.concurrent, all designed to simplify this stuff.
Precisely. Java always had basic threading, the thread class, the synchronized keyword.
The old school way.
Yeah. But this library builds on that foundation significantly. It offers much more flexible, more scalable solutions for those common headaches in multi-threaded code.
Like what kind of headaches?
Things like managing lots of threads efficiently or, and this is a big one, ensuring safe access to data when multiple threads are hitting it at once.
Right. For beginners, I like to think of it, and the source backs this up, like having a pre-built toolbox. Specialized tools ready to go.
That's a great way to put it. You don't have to forge every single wrench yourself.
So why do developers actually use this library so much? What's the big draw?
The primary reason, and the source really emphasizes this, is the simplification it brings. It offers simplified thread management. Things like thread pools, these abstractions that manage reusable threads for you. That cuts down overhead dramatically compared to creating threads manually all the time.
Okay, reusable threads. Makes sense.
But here's where it gets really cool. Thread-safe data structures. Think concurrent hash map or copy on write array list. The latter is brilliant for lists that are read way more often than they're modified.
Okay, so they handle the tricky synchronization stuff internally.
Exactly. You can often share data across threads without writing explicit synchronized blocks everywhere. This is huge. It lets multiple operations happen safely at the same time, reducing bottlenecks.
Like a superpower for your data structures.
Kind of. And beyond that, you get advanced synchronization tools, reentrant lock, semaphore, countdown latch. They give you much finer control than basic synchronized methods.
More flexibility.
A lot more. And then for managing tasks, you have things like executor service and scheduled executor service for running tasks asynchronously, handling complex workflows. It's all built for performance, designed to scale well.
And it's in those real-world applications, isn't it, where this library really proves its worth? Our source outlines some really transformative advantages. What are those actual tangible benefits developers see?
Yeah, the theoretical benefits translate directly into practical wins. First, you get genuinely improved performance. Tasks run in parallel, really using those CPU cores. Think faster data processing, quicker computation.
Makes sense.
Second, and users love this, enhanced application responsiveness. You offload heavy tasks to the background, so your UI, for example, stays fluid. No more frozen screens.
We've all been there.
Haven't we just? Third, efficient resource use. Those thread pools we mentioned. Reusing threads saves a ton of overhead compared to constantly creating and destroying them.
Less churn.
Much less. Fourth, and this is critical, thread safety. The concurrent collections and sync utilities help ensure safe access to shared data. This really cuts down on data corruption, those nasty race conditions.
Ah, yes, race conditions. Fun time.
Not fun. Fifth, you get huge flexibility and modularity. There's a wide range of tools, so you can pick the right one for the specific job. And finally, especially helpful for beginners, it simplifies development.
How so?
Well, these higher-level abstractions hide a lot of the low-level complexity. It helps you avoid common traps like deadlocks, letting you focus more on your application's logic instead of intricate thread management details.
That's really powerful. It makes building these complex systems sound almost elegant in a way.
It can be when
Yeah.
used correctly.
Okay, let's pull back the curtain a bit then. How does this stuff actually work under the hood? What's happening inside the JVM?
Right, the internals. Well, fundamentally, it's about threads managed by the Java Virtual Machine, the JVM. The JVM has a thread scheduler that decides which thread gets CPU time when using things like preemption or time slicing.
Okay, the scheduler's the traffic cop?
Sort of, yeah.
Oh.
Now, for managing those threads, the executor service from the library creates a pool of reusable threads. Instead of making a new thread for every little task, the pool just assigns tasks to threads that are already waiting. Much more efficient.
Got it. The thread pool.
Then you have the concurrent collections, like concurrent hash map. They use clever internal tricks, sometimes called segmented locking or fine-grained locking. This allows multiple threads to access the data, even modify it sometimes, at the same time without messing each other up. Minimizes waiting.
More efficient than just locking the whole thing down.
Much more. And the synchronization tools like reentrant lock. That one allows the same thread to acquire the same lock multiple times without blocking itself. That reentrancy gives you way more flexibility for complex locking scenarios than basic synchronize can offer.
Okay, interesting.
Then you have things like a semaphore, which controls access to a limited number of resources. Task coordination tools like countdown latch let threads wait until a bunch of other tasks are done.
Like waiting for everyone to finish before moving on.
Exactly. And cyclic barrier helps threads meet up at a common point. For really big parallel jobs, there's the fork join framework. It splits tasks into smaller subtasks, runs those concurrently, then combines the results.
The divide and conquer approach.
Precisely. Ideal for certain types of algorithms.
So if we bring back an analogy, maybe the concurrent library is like a really good project manager.
Yeah, I like that.
Expertly assigning tasks to workers, our threads, making sure they don't trip over each other, coordinating everything so the whole project gets done smoothly and efficiently.
That's a pretty good picture. But it's important to acknowledge it's not magic. While it's powerful, concurrent programming still has its challenges.
Right, the source points this out too. It's not all sunshine and roses.
Definitely not. Even with the library, it's inherently complex. Getting your head around thread safety, managing shared resources, it can still be tricky, especially when you're starting out.
And there's overhead.
There can be performance overhead, creating threads, switching between them, context switching, the synchronization itself. It all takes some resources. For very small, quick tasks, this overhead might actually outweigh the benefit of running in parallel.
That's not always faster.
Not always. And crucially, if you misuse these tools, you can run into serious problems like deadlocks. That's where threads get stuck waiting for each other indefinitely.
Gridlock.
Exactly. Or race conditions, where the outcome depends on the unpredictable timing of threads, leading to errors. And debugging these issues, oh boy.
Yeah, imagine they probably don't happen every time you run the code.
Often not. They might only show up under specific loads or timings, making them incredibly hard to find and fix. Also, while the library helps with scaling, throwing too many threads at a problem or using locks poorly can actually lead to contention and reduce performance.
Hitting limits.
Right. And finally, lots of threads consume resources, CPU, memory. You need to manage that carefully so you don't accidentally slow down the whole system.
You mentioned debugging being tough. I think anyone who's chased a race condition knows that pain. So, given these pretty significant challenges, what do beginners really need to know? What's the practical advice for someone wanting to dive in?
Okay, for getting started, the advice is clear and actionable. First, start simple. Don't try to boil the ocean. Begin with tools like executor service for thread pools, maybe concurrent hash map for thread safe data. Get the basics down.
Makes sense. Foundational blocks.
Absolutely. Critically understand thread safety. You have to learn how to protect shared resources, whether that's using locks correctly or leveraging the concurrent collections. Avoiding data corruption is job number one.
Non-negotiable.
Totally. Next, use thread pools. Always prefer executor service over creating thread objects manually. It's just far more efficient. Also, be wary of over-synchronization. Locking too much or locking too broadly can really slow things down. Use the concurrent collections where possible, or finer-grained locks if you need them.
Minimize the bottlenecks.
Exactly. And you absolutely must test for concurrency issues. Don't just test in a single thread. You need to test under load, under different conditions, to try and provoke those tricky bugs like race conditions or deadlocks.
Stress testing, basically.
Yeah, you could call it that. It's also really helpful to learn the key utilities. Get familiar with executor service, concurrent hash map, reentrant lock, count and unlatch. They cover a lot of common scenarios. And finally, start small.
Don't try to build a massive distributed system on day one.
Please don't. Experiment with simple parallel tasks first. Run 2 calculations at once, things like that. Then build up complexity. And looking at real-world use cases helps immensely. See how web servers handle requests concurrently or how data processing systems use these tools.
Okay, that's really solid advice. So, bringing it all together, the core value here seems crystal clear. Concurrency and the Java Concurrent library let you build applications that are efficient, responsive, scalable, really harnessing modern computing power.
Exactly. The library dramatically simplifies managing threads and sharing resources. It's a fantastic toolkit. But, as we've hammered home, you need to use it carefully, thoughtfully. Understanding the trade-offs is key to avoiding complexity and performance traps.
It's a powerful tool, requires respect.
Unpaid.
So the ultimate message for you, our listener, is this. By getting a handle on these concepts, you really gain the ability to build robust applications that juggle multiple tasks seamlessly. Now, what does this all mean for you personally? Maybe consider how these ideas of efficient resource management, parallel execution, might apply beyond just code. How could understanding concurrency help you optimize complex processes in your own work, or even just in daily life? Finding smarter ways, maybe, to do more, do it better, all at the same time. Something to think about.